Hello students, in this video we'll prove the Jensen formula for counting the number of roots of an analytic function inside a disk of a certain radius. So let's suppose this is the Jensen formula. So suppose that f is holomorphic in a disk, so let's say it's centered at 0 of radius r, and continuous, has continuous extension to the closure of this disk, like that, okay? Then, and a1 through an are the roots of f in D0R. Okay, good. Now what we're going to do is the following. So I'm just going to do this up and we're going to derive the Jensen formula. Okay, so what we're going to do is the following. So recall that if I look at my z minus a over 1 minus a bar z, these are my finite Blaschke factors, right? My finite Blaschkes, and these map the unit disk into the unit disk, and they're modulus 1 on the unit circle, and modulus of BA of z is equal to 1 on z equals 1, okay? And what that will allow me to do is, therefore, I can rescale this, and I can say if I look at this function over here, if I look at r squared, and then z minus a over r squared minus a bar z, this will map what? This will map d0r into d0r, like that, and it's going to be equal to r on the boundary, right? N equals r if mod z is equal to r, then modulus of r squared z minus a over what? Over r squared minus a bar z is equal to r, right? And so if I want to make this unimodular, what I can do is the following. So in other words, what I can say is therefore, if I divide by r, this implies, and this is the key trick over here, this says that r and then z minus a over r squared minus a bar z will be equal to 1, right? Just by dividing by one of the factors of r. That's sort of the key feature of this. This is what, when I first read that, when I first understood this proof in Rudin, of course, Rudin's like a fire hydrant. Rudin basically just says, trivially, this is true, right? So work it out yourself, right? It's a very important exercise to do, right? So it's just an extension of this finite Blaschke idea, okay? Great. And so now what am I going to do? So now I'm going to look at f of z. I'm going to look at a function, a new function, construct f capital of z to be f of z, and then times the reciprocal of this product over here, times the product, j goes from 1 up to n, of what? Of just the reciprocal of this thing over here. So it's going to be an r squared minus a j, those are the roots now, z, right, aj bar z over r, and then z minus aj. Okay, that product over there. It's the reciprocal of these Blaschke factors over here. Now, what can I notice about this thing over here? Notice that all the roots of f are over here, right? So this function over here, this function f capital, is 0 free, right? Because I've canceled out all the zeros by putting them in the denominator. Hence, and this is a simply connected region, since the disk D0R is simply connected, I know that log f of z exists and is holomorphic. Beautiful, okay? Now I'm going to apply the mean value theorem to log of f of z. So by the mean value theorem, what can we say? We can say that the log of f of 0 is equal to 1 over 2 pi I, 1 over 2 pi, then you go from 0 to 2 pi of the log of what? Of the modulus of f of r e to the I theta. Beautiful, d theta. Now we can unpack this, right? So unpacking this, what can I say? We know what? We know that the log of f of 0, modulus, is going to be what? Is going to be the log of little f of 0, right? Plus the sum. When I plug in z equals 0 over here, what am I going to have? I'm going to have r over modulus aj plus the sum. J goes from 1 up to n of just the modulus of r over aj, right? If I plug in z equals 0, that's gone over there, that's gone over there. One of the r's cancel, I should have r over negative aj, but of course we're doing modulus. And then of course, what do we know? And we also know on modulus of z is equal to r. If the modulus of z is equal to r, then this factor over here is modulus 1. So all these factors have modulus 1. So when modulus of z is equal to r, this implies that modulus of f of r e to the I theta is equal to modulus of f r e to the I theta. In other words, in this formula, we are going to place this big F with little f. And so therefore, we get the following formula. We have that to the log of modulus f of 0 plus the sum. J goes from 1 up to n, modulus r over aj is 1 over 2 pi, the integral from 0 to 2 pi, of the log of f of r e to the I theta d theta. And that is the Jensen formula. So this is Jensen's formula. That's Jensen's formula over there. And now, of course, what it really does is it basically sort of takes, I need to use the mean value theorem, right? I need to use the mean value theorem, so I had to find something that was zero-free, that was analytic, right? So f was holomorphic over here, right? The whole point now is that I cannot use the mean value theorem if there's going to be some roots embedded in this, right? I have to get rid of those zeros because the function will not be what? The function is not going to be, I can't define the logarithm when there's zeros. If there are zeros in the region, I cannot take a logarithm, period. So I get rid of all the zeros by doing this trick, by multiplying by the inverse of this Blaschke product, okay? That gets rid of all the zeros. Then I can use the mean value theorem. But then in the meantime, I know the Blaschke product has the same value on the circle, right? As a constant value on a circle. So if I'm using the mean value property, I know I can replace the logarithm of the zero-free function with the logarithm of the non-zero-free function by using this Blaschke trick, which is beautiful. And then what's the only penalty that's incurred? The only penalty that's incurred is you have to count the roots, right? But now this provides me with a what? This provides me with a way of counting roots of analytic functions inside a certain disk. And that will allow me to find the genus or the growth order of analytic functions. And using that, I'll be able to prove the Hadamard factorization theorem. Thank you very much.